Hello, this is Dr. Hanaa Assil, and this is the second part of review of Unit 4 in the A2 Chemistry Edexcel. This starts with chemical equilibrium. So we know that chemical equilibrium involves the reversible reactions, which are reactions that go both forward and backward without going to completion. So a reaction like nitrogen plus hydrogen to give ammonia, this will form ammonia, and then the ammonia breaks up to form nitrogen and hydrogen and so on, and this keeps going forward and backward until the reaction reaches dynamic equilibrium. And we should know that conditions for dynamic equilibrium are rate of forward reaction equals rate of backward reaction, and concentrations of reactants and products remain constant. So if we have nitrogen dioxide, it's a brown gas, it could dimerize to form N2O4, which is a colorless gas, but then the colorless gas could break down again to form NO2, which is brown, and we keep going forward and backward until we reach equilibrium, in which we are in a state in between, so that the forward reaction equals the backward reaction. So if we have a question like this, a substance X forms a new substance Y in an equilibrium reaction. In this experiment, X and Y are mixed and react, reaching equilibrium at time t. Which diagram represents the variation in the concentrations of X and Y? Now, of course, if we're starting with X and Y, so we have some X and some Y mixed together at the beginning, but some of the X will break down to form Y, and some of the Y will break down to form X. So at equilibrium, the concentrations of X and Y become constant. Le Chatelier's principle states that if a system is in dynamic equilibrium is subjected to a change, the position of equilibrium shifts in the direction which reduces the change. So we said if we have dynamic equilibrium and then we do something to upset this equilibrium, then the point of equilibrium will shift so that it reduces this change, so that it returns back to the original state. Now, what are the conditions that we could change in order to force a forward reaction or a backward reaction? Remember, we can either change concentrations of reactants and products, so we could add more reactants or remove the products as they're formed, or we could change temperature, or we could change pressure. So what happens if we change each of these factors? So let's say we have a reaction at equilibrium and we want to change the pressure. You have to remember that in any reversible reaction, increasing the pressure forces the reaction to go to the side that has less number of moles. So in this case, if I increase the pressure, it will go forward to form 2 moles of ammonia. Instead of going back, that would form 4 moles of ammonia. So increasing the pressure in this case favors the forward reaction or shifts the equilibrium to the right to give less number of moles. So that's the effect on the point of equilibrium. If we're asking what is the effect on the yield of ammonia, of course, if it goes forward, then it forms more ammonia, so the yield increases. What if we change temperature? In any reaction, increasing the temperature forces the reaction to go to the side that is endothermic. Now, how do we know if it's endo or exo? Of course, from the delta H. So if I have this reaction with a positive delta H, that means the forward reaction is endothermic. In this case, if I increase the temperature, the reaction goes forward. So increasing the temperature favors the forward reaction, which is endothermic, to use up the excess heat. What about the Haber process? The Haber process has a delta H that is negative. That means the forward reaction is exothermic. So in this case, increasing the temperature shifts the equilibrium to the left, or the reaction goes backward. So if we're saying increasing temperature, effect on point of equilibrium, it shifts to the left. Effect on the yield of ammonia, if it goes to the left, that means ammonia breaks up to form nitrogen and hydrogen, so the yield of ammonia decreases, or we have less ammonia. Effect of catalyst, remember a catalyst speeds up the reaction. For a reversible reaction, it speeds up both forward and backward reactions, so catalysts have no effect on the point of equilibrium. If we're talking about concentration, you have to remember adding more reactants or removing ammonia would force the reaction to form more of the product, so the equilibrium shifts to the right in order to form more ammonia. If we add ammonia, that means we're adding the products, or we remove nitrogen or hydrogen, then the equilibrium will shift to the left. So the reaction will go backward, the ammonia will break up to give more nitrogen and hydrogen. So in this question, for example, it says the equation for this stage is this: which of the following would both decrease the equilibrium yield of nitrogen monoxide? So if we have less NO, we want less NO, that means we want the reaction to go back. Which of these will cause the reaction to go back? First of all, should we increase pressure or decrease pressure? We said increasing pressure goes to the side with less number of moles. Now, if I want it to go back, that means I'm going to form 9 moles. If it goes forward, it forms 10. So 9 moles is less number of moles. So in order to go to the side that gives less number of moles, I should increase pressure. What about temperature? Should we use higher temperature to go back or lower temperature? If the delta H for the forward reaction is negative, that means the forward is exo, that means the backward is endothermic. And we said if we increase temperature, it goes to the side that is endothermic. So if I want it to go back, then I want to increase temperature. That means I'm going to increase both pressure and temperature. For this reaction, it says the addition of a small quantity of sodium hydroxide to an orange equilibrium mixture. So we're starting with orange, Cr2O7. Now, if we add a small quantity of sodium hydroxide, now what is the effect of adding sodium hydroxide? Sodium hydroxide is a base. It will react with the acid that is formed as a product. That means I am taking away the product, and that means the reaction will go forward to form more H+. If it goes forward, it will change from orange to yellow. The equilibrium shifts to the right. For each reversible reaction, we should be able to write equilibrium constants. So if I have a reaction like this, Kc is the equilibrium constant regarding concentration. So if we're required to write Kc, the expression for Kc is products raised to their coefficient over reactants raised to their coefficient. And remember, a square bracket indicates concentration. So if I write a square bracket around C, I'm talking about the concentration of C. Kc is called the equilibrium constant for the reaction. Now, for reactions involving mixtures of gases, I can also write Kp. This is the equilibrium constant for partial pressures. So the expression for Kp is the partial pressure of the products raised to their coefficients over the partial pressure of reactants raised to their coefficients. So Kp is the equilibrium constant for pressure, and the P of anything is the partial pressure of that gas. Now, how do we calculate partial pressure? You should know that the partial pressure of each gas is the number of moles of the gas over the total number of moles times the total pressure. That will give the partial pressure of each individual gas. So if we're talking about this Haber process, nitrogen plus hydrogen to give ammonia, if we're required to write Kc, the expression for Kc is concentration of ammonia raised to the power 2, remember we raised to the power of the coefficients, divided by concentration of nitrogen to the power 1 and hydrogen to the power 3. If we're talking about Kp, then it is just the partial pressures. So partial pressure of ammonia to the power 2 over partial pressure of nitrogen to the power 1 and partial pressure of hydrogen to the power 3. So in this question, it says the equilibrium involving this equation, the numerical value of Kp is this. So we're being told that the Kp is 1.8. The expression for the partial pressure of chlorine. How do we get partial pressure of each individual gas? We said it is the total pressure times what? Times, we said, the partial pressure of something is the total pressure times the partial pressure of that. So number of moles or the mole ratio of that. So the number of moles of chlorine divided by the total number of moles times the total pressure, that will give me the partial pressure of chlorine. What are the units of Kp? Remember, Kp, we write the expression, and for each partial pressure, it's in atm. The partial pressures, each pressure is in atmospheres. So if I have partial pressure of R2 raised to the power 8, that's atmosphere to the power 8, over, we have partial pressure of P times partial pressure of Q to the power 3, that's atm to the power 4, and that means the overall units of the Kp is atmosphere to the power 4. Remember that equilibrium constants at a certain temperature are independent of concentration and pressure. The only factor that affects equilibrium constants is temperature. So if we change the temperature, the Kc or the Kp changes. Otherwise, it doesn't. So equilibrium constants would differ from one temperature to another. Remember, catalysts cause equilibrium to be reached more quickly, but they have no effect on the point of equilibrium, and they have no effect on the equilibrium constant. So this question says the Haber process is used to make ammonia from nitrogen and hydrogen at this temperature. When the temperature is increased, what happens? Now, if we increase the temperature, first of all, this reaction, the forward is exo, and we said if we increase temperature, it goes to the side that is endo. So if I have this expression for Kp, the reaction is going back, and that means the partial pressure of ammonia would decrease, while that for the other gases would increase, and that means overall the Kp decreases. The reaction shown is at equilibrium, and the forward is endothermic, which will increase when the temperature is lowered. So if the forward is endo and we're lowering the temperature, we said lowering the temperature to go exo. So actually here, if we lower the temperature, it goes backward. Now what happens when it goes backward? The forward is endo, so it goes backward if we lower the temperature. Now what will happen to that? That means I will have which will increase, so the mole fraction of CO2 would increase. I will be forming more carbon dioxide. Magnitude of equilibrium constant determines the extent to which any reaction can proceed. So if we have a certain reaction and the values for Kp and Kc if they are a small value, then that means that this reaction does not go forward a lot. Because if it's a small value, then the concentration of C and D will be less, and that means that the reaction does not go forward a lot. Water and tetrachloromethane are immiscible liquids. When an aqueous solution of iodine is shaken, an equilibrium is established. So some of the iodine dissolve in water and some of them dissolve in the carbon tetrachloride. And we have the densities. Of course, if we say that the Kc is the concentration of the product over concentration of reactants, and we are being told that the Kc is 86. Now, if we're talking about densities, remember it is given that the density of water is less than the density of carbon tetrachloride, and that means the carbon tetrachloride will be the bottom layer. Now, what happens at equilibrium? Obviously, due to the densities, the water is the lower layer. And it will have more iodine or less iodine. If the Kc is big, then the water layer will have smaller concentration of iodine. Consider the reaction. How are Kp and the mole fraction of PCl5 affected? When the pressure is increased. So we're increasing pressure. First of all, we said if we increase pressure, the reaction goes to the side that has less number of moles. So in this reaction, it will go forward. If it goes forward, then the Kp, first of all, we are not changing temperature, so the Kp does not change. But the mole fraction of the PCl5, if I am going forward, I am forming more PCl5, and that means the mole fraction of PCl5 would increase. Under different conditions, 25% of the moles of gas present at equilibrium is N2O4. So N2O4 forms 25% of the moles. If the total pressure is 380 m, what is Kp? So let's say the expression for Kp is this: partial pressure of NO2 to the power 2 over partial pressure of N2O4. Now, we are being told that 25% of the moles of the gas is N2O4. And that means the partial pressure of N2O4, if the total is 3, then the partial pressure of the N2O4 is 3 times 25 over 100, and the partial pressure of NO2 is 3 times 75 over 100, and that means the value for Kp, when we put these values into the expression for Kp, it comes out to 6.75. Reversible reaction between hydrogen chloride and oxygen produces water vapor and chlorine. Explain what effect, if any, on the yield and equilibrium constants on increasing the total pressure. So if we have this reaction and we increase the pressure, what happens? Increasing the pressure, we said, goes to the side that gives less number of moles. So the reaction goes, remember looking at the equation, if we go forward, it forms 4. If it goes backward, it forms a total of 5 moles. So increasing the pressure goes to the side that gives less number of moles. That means in this reaction it will go forward, so it will form more chlorine. The Kp remains constant because we said the Kp is affected only by temperature. What if we increase temperature? Well, if we increase temperature, the forward we are told is exothermic. That means increasing the temperature causes the reaction to go endo, remember? So it goes to the left since the forward reaction is exothermic. The equilibrium constant will decrease and the yield of chlorine would decrease since we're going back. What about the use of catalyst? Remember, the catalyst speeds up both forward and backward reaction, no effect on point of equilibrium. So the concentration of chlorine and the equilibrium constant will remain unchanged. Remember, when you're writing the expression for Kp or Kc, we do not include solids. So if the equation has solids, we totally ignore that. We said Kp is partial pressure of products over partial pressure of reactants, but we don't include solids, so the only thing included here is the partial pressure of CO2. What about here? We include the aqueous solutions, concentration of silver ions times concentration of chloride ions. We do not mention the solid. So if we have this, what is the expression for Kp for this reaction? If we have any solid, we don't include it. So it is just what? It is the partial pressure of oxygen to the power half. We ignore the solids in the equation. At 680 and 180 m, 52.6% of the molecules in the gas are carbon monoxide. What is the partial pressure of carbon dioxide? Well, you can see that carbon is a solid. We don't include it in anything. So we are starting with 52.6 of carbon monoxide. That means the rest of the 100 is the CO2. The partial pressure of the CO2 is the moles over 100, which is 0.474, because we're saying the total pressure is 180 m. And we said the partial pressure of something is the mole fraction times the total pressure, which is 180 m. So this is the partial pressure of CO2. So that means this is the answer. Remember, when we were talking about entropy, we said the total entropy is equal to R ln K. So the equilibrium constant always increases with increase in the total entropy of a reaction. The equilibrium constant for a reaction always increases when there is an increase in what? Remember, the equilibrium constant increases with temperature only. When the reaction is endo, since increasing the temperature of an endothermic reaction favors forward, so the concentration of products are higher than reactants. When we're talking about we want something that will always increase, that is the delta S total. Then we should know how to write ice charts. When we have a reversible reaction, we write the number of moles at the beginning, number of moles at equilibrium, in order to determine the answer to any question we're asked about regarding a reversible reaction. So if we have this equation, the question says a chemist investigating this reaction started with 5 mole of N2O4, allowed the system to reach equilibrium. So at the beginning, I'm starting with 5 moles of N2O4. I don't have any NO2. Now, the system is allowed to reach equilibrium. If 2 mole of NO2 forms, the amount of N2O4 would be what? Remember that if we have this kind of equation, what happens is X moles of N2O4 will dissociate to form 2X of NO2 from the coefficients. And that means at equilibrium, I'm left with the rest of the 5 for N2O4, and I'm left with the 2X that is formed. Now we are being told that 2 moles of NO2 form. That means the 2X is 2, and that means each X is 1. And I can get that at equilibrium, the number of moles of N2O4 would be 4, while the NO2 is 2. When 0.1 mole of hydrogen and 0.1 mole of iodine were allowed to react according to the equation, 30% of the hydrogen was found to have been converted at equilibrium. The number of moles of each gas is what? Now, if we have this equation, again, if we use the ice chart, initially we started with 0.1 of H2 and 0.1 of iodine. Now, the change should be minus x and plus 2x of HI. But at equilibrium, we're told that at equilibrium, 30% of the hydrogen had been converted. So, if we started with 0.1, 30% of that is 0.03, and that means at equilibrium, I'm left with the rest of that. So, I have 0.07 of hydrogen, 0.07 of iodine, and 0.06 of hydrogen ion. Then we have acid-base equilibria, and you should remember that, of course, acid is the proton donor and the base is the proton acceptor. And we said that if we have an acid with a base, the acid will lose a proton and become what we're going to call the conjugate base, and the base accepts a proton and becomes a conjugate acid. Strong acids dissociate completely, while weak acids dissociate partially. So we have an equilibrium between the acid and its ions. So if we have a reversible reaction, the acid loses a proton and becomes the conjugate base. The base accepts a proton and becomes a conjugate acid. So in a question like this, when concentrated nitric acid and sulfuric acids are mixed, the Bronsted-Lowry acids are which of these? So which of these are acids? The acid going forward is the one that gave up the H+, and the acid going backward is again the one that gave up the H+. So these are the two acids in this reversible equation. Again, when ethanoic acid is mixed, what are the conjugate acid-base pairs? So if we have this, the ethanoic loses the H+, so that's the acid, and the H3O+ going back, that is the one that loses a proton and becomes a conjugate base. So remember that the ethanoic will lose a proton to form base 1, and the acid H3O+ will lose a proton and become base 2. The following equilibrium occurs in liquid ammonia. What is the Lowry-Bronsted acid in this system? Remember, we have two ammonias, so one of them would act as an acid, and the going back, the one that is NH4+ is the one that loses the proton again to form the ammonia. And we should know what is Kw, the water dissociation constant. We know that water ionizes to form hydronium ion. Hydronium ion can either be H3O+, or we could just write it as an H+ and hydroxide ion. At 25 degrees Celsius, the concentration of H+ is equal to concentration of OH-, and this has a value of 10 to the minus 7. This is known. And when we multiply the H+ times the OH-, that comes out to be 10 to the minus 14. This is given the name ionic product of water, or water dissociation constant, which is Kw. And the pKw is minus log of Kw. We should know the word pH actually means minus log concentration of H+ ions. So in water or any neutral solution, the pH is minus log concentration of H+ ions. We said the concentration of H+ ions is 10 to the minus 7. So minus log of that is 7. And that is why we give water the pH 7, because it's a neutral solution. Now, POH is minus log of concentration of OH-. And you should realize again that POH is minus log concentration of OH-, and we said the concentration of OH- is the same, 10 to the minus 7. Minus log of that is 7, and that means if I have pH plus POH, the total is 14. So if we say what is the pH of a solution of sodium hydroxide, and we want pH, the sodium hydroxide concentration of this. Now we know that sodium hydroxide would ionize to give sodium ions and OH minus. Now if we say that the concentration of sodium hydroxide is 10 to the minus 3, this is the same as the concentration of the hydroxide ions, because each sodium hydroxide gives one hydroxide ion. So now we know the concentration of OH minus. We know that H plus times OH minus is 10 to the minus 14. I can use that to get the H plus. I find that the concentration of H plus is 10 to the minus 11. That means the pH is minus log of that, and that comes out to 11. To calculate H plus, remember pH is minus log H plus. So how do I get H plus? It's 10 to the minus pH. So if we say determine the concentration of H plus when the pH is 4, well, concentration of H plus is 10 to the minus pH. So that is 10 to the minus 4. An aqueous solution contains 4 grams of sodium hydroxide in 250 centimeter cubed solution. What is the pH of the solution? Well, we should get number of moles first, mass over molecular mass, and then we want the concentration, and we said concentration of sodium hydroxide is the same as concentration of OH minus. So this will be number of moles over the volume. So concentration of OH minus is 0.4. The Kw is 10 to the minus 14, and that means the H plus would come to be this, and pH is minus log of that. Are we following all of this? Okay, what if we're talking about a weak acid? Now, a weak acid, not all the molecules will dissociate, so we have an equilibrium between the acid and its ions. So equilibrium constant for a weak acid is called the acid dissociation constant, and that is Ka. So Ka is concentration of H plus times A minus over the concentration of the acid. Now remember that the greater the amount of dissociation, the larger the value of Ka. And you should know that P of anything is minus log of that. So pKa is minus log Ka, and Ka is 10 to the minus pKa. Now, to get the concentration of H plus ions for a weak acid, we use this equation. Square root of Ka times the concentration. Remember, the higher the Ka or lower pKa means the solution is more acidic. So if we're asked which one is more acidic, it is the one with lower pKa. When a weak acid is diluted, the percentage of molecules dissociating increases, and that means the pH increases. So remember that a dilute acid is more acidic than a concentrated acid. Adding more water, the equilibrium shifts to the right, more acid molecules break down, so this percent ionization increases. Remember that for weak acid, to get the concentration of H plus ions, we use square root of Ka times C. So when diluted, the concentration decreases, and that means the concentration of H plus decreases and the pH increases. So if we're given Ka and pKa for two acids, which acid is stronger? Remember we said the one that has higher Ka or lower pKa. This is the stronger acid, and that means if I react them together, then the one that is stronger, which is methanoic, is the one that will lose the H plus, and the other one will gain the H plus ions. Titration graphs, you should be familiar with titration graphs. The pH is measured using a pH meter, and the titration is followed using these readings. Now, if we are titrating a strong base with a strong acid, so I have in the flask, I have the base, so we're starting with a high pH. So part A of the graph, this is where we're starting. we have a base in the flask, so the pH is high. And then as we add acid, the pH decreases until we reach a point B where there is a very fast decrease in pH. This is called the equivalence point. So the pH halfway through B is the equivalence point, and this is where the indicator we're using should change color. So if we're asked which indicator to use, we want something that will change color at the pH in B. Any more acid after that means excess acid in the flask, and that means the pH will go down to the pH of the acid. This is a table present in your data booklet, and this will help you to choose the correct indicator for each titration. So the indicator shown should be the one that changes color at the equivalence point. So again, when we were talking about strong acid with strong base, we said the equivalence point will be at around pH 7. So titrating sodium hydroxide, for example, with HCl, which indicator should I use? I look for something that changes color at around pH 7. So bromothymol blue would be a good choice. If we're titrating strong acid with weak base, that means I'm starting with a pH of about 11 or about 10, then we're using a strong acid, so eventually I will end up at pH 1 or below. Now, where is the equivalence point? It's in the middle of that point, so it's around 4 point something. I look at the table, where is the indicator that changes around that? So that is methyl orange. Weak acid with strong base. Weak acid means I will end up with a pH around 4 or 5, but I'm starting with a pH of about 13. Where is the equivalence point? It will be around 9, for example. So I'm looking for which indicator would be suitable. That would be phenolphthalein. What about if I have a weak acid with a weak base? Remember, weak acid with a weak base, there is no sharp fall in pH, so no acid-base indicator is suitable. So usually we don't do this kind of titration. So in general, you should remember, if I'm titrating strong acid with strong base, bromothymol blue is probably a good choice. Weak acid with strong base, you could use phenolphthalein. Strong acid with weak base, you could use methyl orange. And remember the colors, and you can get all of this from the data booklet. What if I have a diprotic acid? Diprotic acid means I have two H pluses that I'm trying to titrate with the acid, with the base. So I will have one jump when the first H plus is neutralized, and another jump. That means I have two what we call bumps in the graph, and that tells me that I have two replaceable H plus ions. A base also could be with two protons. So we have this base such as diamine. When I titrate it with dilute HCl, I am titrating one of the amines will take H plus, so that's one decrease, and then the second amine will take the second H plus. So these graphs, please be familiar with these graphs, and you should be able to think about how to draw them even if you don't remember them. And remember, strong acid with strong base, equivalence is at pH 7. A strong acid with a weak base will have a pH lower than 7. A weak acid with a strong base would have the equivalence point at a higher pH than 7. So if we say 1.1 mole per decimeter cube sodium hydroxide is titrated with ethanoic acid, so this is what? A strong base with a weak acid. Which one would be the best indicator? So strong base with weak acid, we said that means the equivalence point is about 7. Which one is above 7 or around 8? That would be phenolphthalein. In acid solution, methyl orange is red. When an alkali is added, the solution turns yellow because what happens to the indicator? Remember, the indicator changes color because it loses H plus ions. So remember, why does the indicator change color? Because it loses H plus ions to form anions. Which two solutions, both of concentration, same concentration, have been used to produce this titration curve? Well, let's see. Where is the initial and the final, or where is the equivalence point? So this is something starting from pH 4. pH 4 is a weak acid, so I'm looking for something that has a weak acid. So it is HCOOH, not HCl. And I want something that will end up at pH 14, that is a strong base. So a strong base would be KOH, not ammonia. Which curve would be obtained for the titration in which hydrochloric acid is added to aqueous ammonia? Well, let's see. Added to aqueous ammonia means I'm starting with ammonia. That means I'm starting with a pH that is about 10 or 11. And I want to end with hydrochloric acid, which has a very low pH. So this would be the correct graph. Please note this question. It says carbonic acid forms two types of salts, carbonates and hydrogen carbonates. A solution of sodium carbonate is titrated with hydrochloric acid. On the grid below, sketch the likely shape of the titration curve. So remember, we are talking about a diprotic acid. And the information given is carbonates require 2 moles of H plus ions per mole of carbonate for complete reaction. 10 centimeter cubed of sodium carbonate with a concentration of 0.1 mole per decimeter cubed is used. The sodium carbonate solution has a pH of 11.3. 40 centimeter cubed of HCl with a concentration of 0.1 mole per decimeter cubed is added, and we're given the pKa for the first H plus and the pKa for the second H plus, and we're required to clearly label any equivalence points in the checks. How can we draw this? Let's take a look. First of all, we have carbonate in the flask, so a solution of sodium carbonate, and that would be a pH, it states in there that the sodium carbonate has a pH of 11.3, so I have to start from 11.3. Then we're titrating with HCl, so we're going down until the pH of the equivalence point. It says 40 centimeter cubed of hydrochloric acid with a concentration of 0.1 mole per decimeter cubed is added, and that means if I have a total of 40 was added, it says at the beginning actually 10 centimeter cubed of sodium carbonate with concentration of this is 0.1 mole. So anyway, first of all, the graph must have 2 bumps because we have 2 replaceable protons. It has to start at pH 11.3 because it says there that the sodium carbonate solution has a pH of 11.3. Now, what is the final pH? The final pH is minus log of the H plus ions. How can I get that? The H plus ions have a concentration of 0.1, so I have to end at the end down there at pH 1. And then, what is the number of moles of sodium carbonate? It says I had 10 centimeter cubed of sodium carbonate, concentration 0.1. So this is the number of moles of sodium carbonate. Now, the number of moles of HCl that I need to neutralize it is 2 times that, because I need 2 moles of H plus to neutralize the carbonate. And that means that the number of moles of HCl I'm going to use is 0.002. So the volume of the HCl that will neutralize that first amount is, actually all the amounts is 20 centimeter cubed. So my equivalence point for the second bump has to be at 20 centimeter cubed. And that means the equivalence point for the first H plus would be half of that, and that is at 10 centimeter cubed. What about buffers? You should know buffers are solutions that resist a change in pH when small amounts of an acid or a base are added to them. So buffers are usually solutions of a weak acid and its conjugate salt. So for example, if I have a mixture of or a solution containing ethanoic acid and sodium ethanoate. Now the ethanoic acid ionizes partially to give H+ ions. The sodium ethanoate would ionize completely to give the sodium salt. Now the buffer is made up of a solution that has high concentration of the acid and the conjugate base. So if we have this in solution, we have both of them in solution. Now when we add H+ ions, a small amount of H+ ions to the solution, that means I'm adding the H+, that's a product in this reaction. That means the equilibrium will move to the left to use up the excess H+ ions. If we add OH- ions, a base, a small amount of base, it will react with the H+. So it is as if it's removing the H+ from the mixture, so some of the ethanoic acid will dissociate and the point of equilibrium goes forward to form more H+. Now, a more concentrated buffer has more resistance to pH change than a less concentrated one. So if we have two buffers, the one that is more concentrated is a better buffer. Now, in buffers, these are the equations that we use. pKa is minus log Ka, and then we put it into this equation. We can use one of them, either pH is equal to pKa plus log of the base over the acid, or minus log the acid over the base. So, a buffer solution is made by mixing ethanoic acid and sodium ethanoate in a 3:1 ratio. Ka for ethanoic is this. What is the pH of the buffer? Okay, so pH is pKa plus log of the concentration of the ethanoate over concentration of the ethanoic. So if he says that it is a 3:1 ratio, then the pH is minus log the pKa that is given plus log 1/3. So this gives a pH of 4.3. This question says, which of the following solutions when mixed would make a buffer with pH greater than 7? Of course, pH greater than 7 means I need a weak base, and this would be the ammonia with the ammonium salt. The titration curve is shown. Which region of the graph represents the effective buffer region? Remember, if you're looking at a graph, which part is the buffer region? It is the part where there is very little change in pH over a long period. So the region U, the pH changes slightly over a big volume of HCl being added. So this would act as a buffer. A buffer was made by mixing 20 centimeter cubed of 0.05 mole per decimeter cubed sodium hydroxide and 20 centimeter cubed of 0.25 mole per decimeter cubed propanoic acid, and we're given the Ka. Calculate the pH of this buffer solution. So we're adding a certain amount of sodium hydroxide to a certain amount of propanoic acid, and we want to know its pH. So what we have is propanoic acid plus sodium hydroxide to give sodium propanoate plus water, and we know that the Ka of that acid is the concentration of H+ times concentration of the propanoate over the concentration of the propanoic acid, and we are given that the Ka is 1.3 times 10 to the minus 5. Now, calculate the number of moles that we added, concentration times volume. The number of moles of acid that we added, concentration times volume. And then I want the number of moles of the salt, that is sodium ethanoate, which is the A-, that would be the same as the number of moles of the sodium hydroxide. Then concentration of each of these would be the number of moles over the total volume. Remember, we added 20 of sodium hydroxide to 20 centimeter cube of propanoic acid, so the total volume is 40 centimeter cube. This gives the concentration of the propanoate, number of moles of acid left in the mixture. We still have some acid in the mixture. That is the rest of the number of moles that we had. Remember that the equation says if I have 0.001 mole of sodium hydroxide, I need only that same amount of moles of the acid, but we added 0.005. So the remainder of that is 0.004. Now the concentration of the acid that did not react, which is still in solution, would be the number of moles over the total volume again. So now we have this concentration. So the concentration of H plus we can get from the Ka, the expression for K up there, Ka times the concentration of the acid over the concentration of the propanoate. This gives concentration of H plus ions, and the pH is minus log of that. Explain how this solution acts as a buffer. So if I have this solution and we're asked to explain how it acts as a buffer when a small amount of alkali is added. Remember, we said the mixture contains a large amount of acid and its salt. The hydroxide ions reacts with H plus, removing it from solution, and this causes the equilibrium to shift to the right to make more acid. The pH does not change since the change in concentration of salt and acid is very small. Okay, remember that we need to keep the pH of blood constant, so we have buffers in the blood like hydrogen carbonate ions that help to keep the pH constant. You should know the role of hydrogen carbonate ion in maintaining the constant pH. For example, this was a question that said sodium hydrogen carbonate is part of a buffer in the body that controls the pH of blood. Two of the equilibria involved in this process are this. So the hydrogen carbonate reacts with hydronium to give carbonic acid plus water. The carbonic acid then dissociates to give CO2. Use the equilibria to explain how the buffer keeps the pH of blood nearly constant when a small increase in concentration of hydrogen ions occur. So if we're adding H plus ions, then there is originally a large concentration of HCO3 minus. So this reacts with the excess H plus ions so that equilibrium moves to the right to use up the excess acid. Now that means more H2CO3 is formed. The equilibrium 2 moves to the right to form more CO2, so this is released out of the body. The pH of a blood sample was found to be this. Calculate the ratio of concentration of HCO3 minus to H2CO3. We have this equation and we have this Ka. So if we have pH, I can get concentration of H plus ions, 10 to the minus pH. And then in this equation that he gives me, the Ka is HCO3 minus times H plus over H2CO3. Remember, we do not include water in the expression for Ka. So from that, I have the Ka and I can get the ratio of the concentrations of HCO3 minus to H2CO3. Remember, the calibration of a pH meter is best carried out using which of these? When we want to calibrate a pH meter, alkaline and acidic buffer solutions are required to calibrate the pH meter to ensure that it is calibrated across the pH range. Okay, so we will stop here for this part of the review, and we will continue in the next review the organic chemistry and the spectroscopy. So thank you for listening.